Okay, good. So, people at the back, although my voice will carry because of this, my board work is not very good, I realized from the last lecture. So, if you actually want to see what I'm writing, maybe you want to come a little later. But if you want to sit there, that's fine. Okay. So, let me sort of sketch what I want to do today. So, the last lecture was sort of all about trying to say you actually have a system of interacting electrons. Where do these localized moments come from? And we agreed that the right way to think, if you're talking about very insulating materials, is to integrate out the charge fluctuations. And then what's left behind is the physics of spins. And we tried to develop a systematic expansion, which goes back to the work of Thouless and even before that Heisenberg and Dirac, for writing down these effective Hamiltonians for the spins in terms of exchange operators. Right? That was what we did. And in the process, we discovered that the kinds of terms you get involve nearest neighbor Heisenberg interactions on any lattice, which basically are in the SU2 symmetric case. You also get 3-particle exchanges or a ring exchange between 3 spins, sigma 1, sigma 2, sigma 3, going to sigma 2, sigma 3, sigma 1. But this can be written in terms of the same operators. They lead to corrections to the nearest neighbor exchange terms. You get more unusual terms which involve exchanges of 4 spins. And things like this. And at larger and larger orders, you will get more and more complicated terms. But of course, if your premise is that you're starting with a very insulating material, these larger and larger terms are expected to be more and more unimportant. So you shouldn't expend too much energy working them out to very high orders. But for example, there are materials where the analog of this process is believed to actually control what happens at low temperature. And these are some organic compounds which appear to have a spin liquid state. And I'll talk a little bit about them in the next lecture. Because this lecture I want to focus more on the effects of, so that would be the effect of higher order ring exchanges. Today's lecture I want to focus more on the idea of geometric frustration that arises even in simple systems like this if the geometry of the lattice is such that it makes different bonds compete with each other, right? And in the tutorial yesterday, Shubhro told us how if you have strong spin orbit coupling at the atomic level, this modifies even the leading order exchange interactions to produce other terms, because SU2 is no longer a good symmetry, spin is not conserved, it's the spin and the orbital angular momentum together that are conserved. So you get terms apart from this, you get terms which are on a bond, Dij, and you get the symmetric and this is somehow I'll call it D2, which is a traceless symmetric tensor that combines with this combination. The trace part of it just renormalizes this. That's what Shubhro showed me, right? So the message here was that there's all sorts of other complications that arise if there's spin orbit coupling. The one thing he left out is perhaps the simplest thing that can happen, which happens many times, which we will talk about, is simply that because of crystal field effects and the total moment not being a spin, but a spin plus an angular momentum because of orbital intricacies, the spin just likes to orient in some direction. So although the exchange interaction is like this to leading order, there is just a local term that says each vector likes to point in some particular direction or in some plane. So those are local single ion level anisotropies that also will play a role, and today we'll discuss them. So this is what we got to last time. So let me just elaborate on this geometric frustration thing first. So these are the first two things we talked about. So if you have a nearest neighbor exchange interaction on any bipartite lattice, then you can actually find the global minimum the global minimum of energy, thinking of these as classical vectors to begin with, is achievable because on each bond things like to be anti-parallel, and if you have a bipartite lattice, you can simply set one sublattice of spins, the A, to be along some spontaneously chosen direction and the other in the opposite. And this is the nail state. This pattern is the nail state. And it's a good solution of the classical problem. And then the question arises, do quantum fluctuations destroy this? And you can work this out systematically in 1 over S expansions. We'll talk about that in a little bit. And the conclusion is that even in 2 dimensions, the ground state remains nail ordered when you have a bipartite system and you include quantum fluctuations all the way down to S. Okay? So this classical way of thinking works really well for bipartite magnets, as long as there is nail order and no frustrating higher order terms. So for bipartite magnets, it's higher order terms that can destroy things. There's nothing that happens because of the nearest neighbor. But the situation is quite different even at the classical level. And today we'll mainly talk about systems that can be thought about classically to sort of warm up to tomorrow's lecture. So even at the classical level, if you have nearest neighbor antiferromagnetic exchange on non-bipartite lattices, the situation is much more confusing, not so clear what the answer is. And that's because although each bond would like to minimize its energy by doing this, the bonds are arranged with triangular motifs in the unit cell. And there's no way you can achieve a state that does this on every bond, right? So then the question is, what's the next best thing the system can do? And so the system needs to compromise at the classical level. It can't lower its energy all the way down to the global minimum. So what's the next best thing? So that can lead to lots of interesting effects because the next best thing can involve massive degeneration. So let's take a really simple example. Let's take one tetrahedron. And the classical energy is just the sum over all the bonds. These are thought of as vectors of length S. Right? So now you can sort of do some counting of constraints. So you have 4 vectors, all of which are unit vectors. So that's 2 degrees of freedom per vector. There's 4 of them. That's 4 times 2, 8. Right? I've incorporated the unit vector. But then there's a vector constraint that says, because I can rewrite this as a perfect square, I can write it up to a factor. I can write it as constant plus something times sum over I Si square, right? So that implies that whatever ground state I'm looking for, the best I can do is set the vector sum of all the spins to 0, right? So that's one vector constraint. That removes 3. So it looks like you have lots of freedom. You have 5 continuous degrees of freedom. But of course, some of these involve just a global choice of coordinates. You know, where you put your z-axis and then where you put your x-axis. So that you subtract another 3 from to get 2. So there are 2 continuous degrees of freedom here. So there's a 2-parameter manifold of configurations of these 4 vectors that will minimize the energy. Now if you have a big lattice which is made up of these tetrahedral motifs and you have thermal fluctuations, who's to say what the spins do? Right? So that's the complication even at the classical level. Usually we are used to thinking of classical statmech as being relatively simple to visualize, imagine, because you just look at the energy function, find out what the minimum is, and then it's a competition between energetic effects that try to achieve that minimum and entropic effects that like to gain entropy by fluctuation. And we know how to think about that competition. But here that first effect is simply not there. What's left behind is this large sort of manifold of states about which you fluctuate. So which particular state is chosen is not clear at all at this level of argument. Right? And it's going to obviously depend very, very sensitively on things I've left out of the discussion. Biggest thing I've left out is quantum mechanics. Right? We'll talk about that. But also subleading interactions and any imperfections will dramatically affect what happens. So that's sort of why even the classical problem is of some interest. If you do the same counting on a triangle, so just a single triangle, the same counting gives 0, right? So there's no degree of freedom left, and that's indeed true. We know that for a single triangle, the best you can do is pretty unique. You take 3 spins and put them in a coplanar state, which is 120-degree angle with each other. So what's involved is a spontaneous choice of a plane. So you, instead of choosing a spontaneous direction, there's a spontaneous choice of a plane, and then there is a spontaneous choice of orientation within the plane. And once you do that, you have subject to up to global symmetries, you have a unique state. So this problem you can now start thinking about by standard methods, just like you do for the bipartite case. You start with this set of this configuration, and you ask if quantum fluctuations destroy it, and it will turn out that if you actually do the 1/s corrections, you find that this long-range order is preserved at 0. So this is sort of the single triangle tiling. So go from this to the triangular lattice. And at the level of the nearest neighbor Heisenberg model, there isn't too much mystery about what happened. So here, if there's something interesting happening, it would be because it's not a very good Mott insulator, and there are higher order charge fluctuations that play a role, like the ring exchange. We discussed that. Okay? No, well, I wouldn't. So it is frustrated in the sense that you can't achieve the nail state, but it's not strongly frustrated in the sense that at the classical level, there aren't lots of these. Right? And so there's at least a starting state from about which you can put in quantum mechanical effects and ask if that starting state is preserved. And the answer is it is preserved, as long as you don't include any higher order process. Now, here's an interesting thing already at the level of a single triangle. If instead of having isotropic spins, Js dot S, you had one of these systems with strong spin orbit scattering effects at the atomic level, so that the system, the spins picked out an easy axis. So if you had a Hamiltonian, which was just the Heisenberg exchange, except for the fact that there is, for every spin, a preferred direction in spin space. Right? A single ion anisotropy. So this, of course, makes no sense for spin half, but this anyway won't exist for spin half because you don't have these kind of terms. Right? So we are talking about these atoms with a lot of orbital degeneracy and spin orbit effects, so that the spin I'm talking about is actually the total J. And its crystal field effects then and the details of the configuration of the crystal that determine what anisotropy is. This is a sort of a symmetry, generic symmetry allowed choice in many cases. And if you had this, for example, on the triangular lattice, so even at the level of a single triangle, it's clear what the difference is. Here there was a unique state up to global symmetries. Here there isn't, because you need one minority spin, which can be here, or into other places. So there's a threefold degeneracy here, even at the level of a single triangle. And of course, there's a global spin flip, but that's a global spin flip, right? So unlike the isotropic problem, even the classical triangular lattice magnet, if you took one component spins that can only point up or down, has a massive degeneracy. And these are all accidental degeneracies. They are not related to any global symmetry, right? They are symmetries that come from fine-tuning of terms in the Hamilton. There isn't a symmetry interpretation of them. They are not symmetry. The different configurations that all have the same energy are not symmetry. So this is actually a very common sort of model for several real materials. So let me use that as an opportunity to introduce some materials and lattices. So first example is, like I was talking about, triangular lattice. This is simply the standard triangular Bravais lattice in 2 dimensions. And each site can host a magnetic ion. One of the best studied examples is a certain polytope of silver nitride, where nickel 2 plus is spin 1 and is described by an effective Hamiltonian at low energies that looks more or less like this. With the easy axis that's common, all the Ni point out of the plane. So all Ni, all easy axes. And D is comparable to J. And so you might want to start by thinking about it in the Ising limit. There are complications in this material having to do with further neighbor hops that are presumably generated by some higher order processes. So we won't discuss it in detail, but this is just an opportunity to say there are many materials with this kind of structure in the effective Hamiltonian. And maybe this is also a good time to make one comment. In yesterday's lecture, I may have inadvertently given the sort of impression that you must actually calculate these coefficients exactly right, and then you can fit to data. That's never usually the case. The problem is not with the validity of the expansion I derived. That's just straightforward perturbation theory, you know all the factors. The problem is with the starting model. So we wrote down a Hubbard model with some T and some U and then started working. You never know enough about the actual first principles calculations of these materials to extract from it very accurately a T and a U that will go into a Hubbard model. So it's the writing down of the Hubbard model that involves the greatest degree of uncertainty, I mean from first principles. So you can't really ever calculate exchange constants very precisely. So for example, how do I know that there's a second neighbor exchange in this silver nitride compound? You know it by fitting experimental data to a model. And the cleanest version of this is actually a very neat thing. So supposing you had exchange couplings, let's say the exchange energy is 10, 15 Kelvin, not huge numbers like 100 Kelvin, okay, in temperature. Then you'd like to extract what the exchange constants are without any assumptions from some experiment. So the neatest thing you can do is just apply.
Hello, mic test. Hello.
What?
Hello.
Where is that coming from?
ಇಲ್ಲಿ ಕಂಟ್ರೋಲ್ ಇಲ್ವಾ? ಇದರಲ್ಲಿ ಕಂಟ್ರೋಲ್ ಇಲ್ವಾ ವಾಲ್ಯೂಮು? ಹಾಗೆಲ್ಲ ಫುಲ್ ಡೌನ್ ಮಾಡಿ.
Okay.
Full down.
apply a large magnetic field so that the Zeeman energy is much bigger than the scale of the exchange constant. Now, whatever was the low temperature state of the original material, once you apply a field this large, the Zeeman energy will overwhelm all exchange energies and the system will just polarize fully. So you begin with now a state which is just everything pointing along the field. Right? Even if I flip one spin, that's going to cost some energy. Right? In fact, that flipped spin is like a particle. Right? It's the quote-unquote quasi-particle excitation of this ground state, the polarized ground state. And what the exchange constants are going to do is they're going to make that particle hop, right? Because that's what exchange is. If this spin is down and that's up, after exchange, the down spin goes there, the up spin comes, right? So your exchange energy or your exchange constants, the first neighbor, second neighbor exchanges, the ring exchange, everything, they will in effect become the sort of parameters of the band structure of this single particle that's hopping in some lattice, right? And by looking at the inelastic neutron scattering data, you can actually pick out these modes which correspond to propagating particles which are flipped spins and work out what their band structure is from the data and fit that band structure to a first neighbor, second neighbor, third neighbor kind of exchange model. And that's, in the cases that can be done, that's often the most accurate way to know what the exchange constants are. Okay? If you don't know that, then you have to make some ansatz about what the low temperature state is and then fit the excitations of that state to your data. But you never can calculate them most of the time. Ring exchange, I doubt. But you can work out further neighbor exchanges, which are often quite important in these complicated geometries. For ring exchanges, you have to look at line shapes of magnons and decays and things like that. Okay. So this part of the board I should leave untouched, right? Go back there. Okay. So let's leave this and go there. I should start the clock, right? When did I? Okay, let's stop. Here. Start. Okay. So that's how you know in this material, for example, that there's a sizable second neighbor exchange which changes the physics. The other sort of very well-known example of a three-dimensional lattice on which there are many materials which have this sort of physics is the pyrochlore lattice. And this is the lattice that's involved when you think about the physics of the magnetic ions in materials like holmium titanium. So here you have holmium 3+, which is a rare earth and subject to the kinds of strong spin orbit effects that Subro was talking about last time. And this has a L plus S, the total J, which is our effective spin, very large, 8 in this case. That's your S, effective. And here the exchange energy scale is only 1 or 2 Kelvin. And this single ion anisotropy D is, 40 or 50 Kelvin, much larger. And the axes along which the spins like to lie parallel or anti-parallel are not the same throughout. This is a three-dimensional structure. On symmetry grounds, it's not easy to imagine everybody having the same common easy axis. So let's draw out this because it's going to be of relevance later. So one way of imagining what the pyrochlore lattice is to first imagine that you're looking down on an array of tetrahedron. Okay? So let's do it like this. So this is a tetrahedron. This is the base of the tetrahedron, and this is the apical side which would come out of the board at you. Okay? And if I get this right, this is the next one. The same kind, apical side coming out, and then a base. Here maybe. Here's the third one. Okay. Now these share sites, these base sites, with another array, another interpenetrating array of tetrahedra that are pointing down or into the bowl. So let's draw them like that. And the out of plane site of this one goes behind the blackboard. And clearly I can continue this in the plane. The basis of these tetrahedra up and down can be continued in the plane into a nice lattice, which is a planar lattice of corner sharing triangles. So basis make lattice of corner sharing triangles. And this is the Kagome lattice. Now, I've said this is a three-dimensional structure, so how does this continue? Well, the way it continues is this site, which has come out of the bowl and is the apical side of this tetrahedron, is now the apical site also of a down-pointing tetrahedron that comes out into the next layer, like that. So let's draw that. So this is coming out here, the triangle. That sits here, and in the middle there is this side that's shared between this triangle and that side, right? And the same thing here. And the same thing here. So this is the next layer coming out of the board, right? And they have their own, I don't know what, maybe use a different color. Interconnections like that. This is the next layer now, right? Which will have another up pointing thing coming 3 layers up, right? Blackboard was the first layer. This dotted stuff is the second layer, including this. And this cross is now the third layer. And this continues, right? So what you've really got is sort of layers of this Kagome lattice that talk to each other via these apical sites that are shared. And the apical sites are only shared between one sublattice of triangles, up-pointing triangles in the outward direction, the down-pointing triangles in the backward. So that's the lattice. It's a complicated lattice, but I think this is perhaps the simplest way you can even try and visualize it on the blackboard. Doubt there's anything better. But now the point of doing all this was to say there's a natural choice of easy axis dictated by crystal fields and geometry, and that's simply the body diagonals of the tetrahedron. So if you have a tetrahedron, and there's the center of the tetrahedron, and there's a diagonal going through the site that goes to the center of the other tetrahedron which is shared. So you take centers of neighboring tetrahedra and join them, going through sides. Those are the body diagonals. And those are the natural easy axes. And indeed, if you look at what the spin Hamiltonian is, this large anisotropy is forcing the spins to lie along that axis, either up or down. So that's another example where this simple easy axis kind of effect is more important than all the other complications that we know of. How am I doing on time? Actually, that's very inaccurate. I started halfway through. Okay. 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 Yeah, that's okay. So I should mention this pyrochlore lattice is part of this structure. For example, holmium titanate is part of a larger family of materials, oxides, with this formula. And both the A and the B sites of this class of materials form these pyrochlore lattices. They are just shifted from each other and interpenetrating in some. So if one of the A or the B sublattices hosts a magnetic ion, like in this case, holmium is magnetic, titanium is not. Titanium is, I guess, nominal valence of 4. Yeah. So 4 times 2, 8, 3 times 2, 6, 7, correct. So that's totally non-magnetic. So that's why you get this simple pyrochlore magnet. If you had both magnetic ions, you would get something far more complicated to think about, and we won't go into that. So you have A-site pyrochlores, which means there's the magnetic ions here, or the other way around, or both sometimes. Since I've already introduced the Kagome lattice, which is just this planar array of corner sharing triangles, I should mention that there are several materials where there's strong anisotropies coming from spin orbit effects on the Kagome lattice. One example I'm familiar with is a neodymium compound. Again, Js square is much smaller, 2 to 3 Kelvin compared to D, which is 10 Kelvin. And the point about sort of belaboring this is to say that if you had this Hamiltonian, and D was really much larger than J, then there's an obvious starting point, and the obvious starting point is to just project this Hamiltonian into the subspace of states that is favored by this interaction, which are just the maximally polarized states up or down along this n axis. Right? So Sn equal to plus minus S would be the states that you project into. And that would be the leading Hamiltonian. Regardless of what quantum mechanics does, the first term you get is just the classical Ising model on this lattice. So project, and you get an effective model, which is just J S square dot product of these angles, of these unit vectors that are the easy axes, and then some classical variable which you could call sigma z. So you get a classical Ising model, and the exchange, the sign of the exchange actually depends on what the easy axes are. So for example, in the pyrochlore case, the holmium titanate, it's believed that the bare value of J is actually ferromagnetic. But because there's such a strong easy axis, and the easy axis is along these body diagonals, this angle being obtuse, this gives you minus sign, and so it converts ferromagnetism to antiferromagnetism. And so the ferromagnetic exchange interaction in holmium titanate converts to an antiferromagnetic Ising model on the same time. So there is some sort of class of compounds where just the Ising model is a good starting description. So look, you can imagine quantizing this spin along any axis, any orthogonal set of axes, right? There's no need to just go C, X, and Y. So let's quantize it along the n hat axis, right? So if you quantize it along the n hat axis, there's one term which is the component along the n hat axis talking to each other. And then there are the components that flip that spin, right? Just like you have transverse exchange, yeah. So anything that flips this spin is going to take you away from this plus minus S manifold, because you will either go from S to S minus 1 at a site or minus S to minus S plus 1, right? And so the low energy effective Hamiltonian, just like we derived for the Hubbard model, would involve some further processes that come back down to this manifold. Those would be higher order corrections. But the leading order answer is always you project your perturbation in the degenerate subspace. That's the standard result of quantum mechanics, right? Standard perturbation, first order. So you just project this perturbation. This is the Hamiltonian now, and that's the perturbation. You just project it, and what survives is just this much. Right? There'll be other terms that will correspond to quantum mechanical processes that will add complications, and we'll talk about them tomorrow a little bit. But to begin with, you just have this. And then there's another class of examples which seem to be completely isotropic as far as we can tell. Typically chromium 3+, for example, the spin 3 halves is just, really well modeled by just the isotropic exchange term. And it's higher spin, it's spin 3 halves. And so again, you might be able to think classically. So there's a class of materials for which thinking classically actually leads to fair amount of insight and not too bad an approximation when it comes to modeling real materials. These spin-ice materials are the best example of that. There's a huge amount of work experimentally. Shubro, I think, has these things. Yeah. Okay, so that was sort of the general background. And with this background, I'm going to start. So I've talked about these massive degeneracies that arise because of competition and how they complicate our thinking even in simple classical context. So I want to put some flesh on it by discussing a case where we actually know the exact answer from a solution dating back 70 years. But we are going to try and obtain the essential features of that solution by doing no complicated calculations, but thinking in terms of some effective field theory or effective model. Okay. So that's the next thing we'll do. So let me go there and start again. Let's consider the simple triangular lattice Ising antiferromagnet, which is just Ising variables living on this lattice. And as we've already discussed, even at the level of a single triangle, there are 6 states that minimize the energy. So let's start with some state. Okay. So you see, by making some choices, I've made sure every triangle except this one. So this one has 3 upspins, so that has too many frustrated bonds. I could have done better. I could have had only 1 frustrated bond. But in all the rest of them, I think that's true, I have exactly 1 frustrated bond. Right? And that's the best you can do. You can put 1 frustrated bond, which means 1 bond where the spins along the bond are parallel to each other. If you have 1 such bond, you can have 2 which are anti-parallel, and that's the best you can do. Here I kind of spoiled my chances of doing that by making all of them possible. Okay, so there's a simple characterization, visual characterization of the possible states that are lowest in energy, and they come by drawing the dual lattice, whose sides are these crosses, and connecting these crosses by links that are perpendicular to the original links of the triangular lattice. And this way you get a honeycomb net or the graphene lattice, right? And now the rule is that every time a honeycomb link crosses a frustrated bond, you put a dimer on it. You put a hard rod on it, like that. Here I have to put 3 hard rods, but everywhere else, every other side of the honeycomb net gets touched only by 1 hard rod. So for example, which one? This one? Well, I want it the way it is, I think, because I want to do this, right? And then I want to do this, and this. So you can see every other side of the honeycomb net got touched by exactly 1 rod, except the site that's at the center of this fully frustrated triangle, where none of its links are obeying the antiferromagnetic exchange energies preferences, right? So if you want to look at the low temperature behavior, you will have very few of these and a lot of those. And at 0 temperature, strictly, if you want to just count the degenerate ground states, you will have none of these, right? So you will have so T equal to 0, T going to 0, number of defective sites vanishes, and every dual site touched by exactly 1 dimer. So if you want to count how many ground states there are of the classical Ising model, you count the number of perfect matchings of the honeycomb lattice, which is a well-known problem in computer science or combinatorics. You know that the number will scale with the volume of the lattice, with the number of sites in the lattice. And so there's an extensive ground state entropy for the classical model at 0, right? Coming purely from these accidental degeneracies. Different states that are part of this ground state sector are not connected to each other by any symmetry. They are just accidental degeneracies. So this, now if you're at non-zero temperature, apart from this dimer subspace, you will have these defects, right? But you can never have a defect where a site is touched by nothing, okay? I mean, you can study dimer models that do that, but they're not relevant to the physics of our Ising model. And there's a reason. The reason simply is if you take any circuit on the original lattice, you start with this spin, you go here, you go there, and you come back. You must get back to the same spin, obviously. That means the number of spin flips you encounter must be even, right? So you can never have, and since there are 3 links here, the number of spin flips is even, the number of frustrated bonds must be odd, right? So you can have 1 or 3, but not 0 or 2, right? And this argument also works for, so supposing you put this triangular lattice, the original magnet, on a torus. Right? Let's say you chose these as your principal. Okay, let me draw this better. So let's say I took my triangular lattice and put it on a torus, so that I identified this with this and that with that, right? This is one of the directions of the triangular lattice. That's the other. The third one is in the middle. So you could imagine walking along this line of Ising spins and coming back to the original spin. You must get back the same spin. So again, the number of spin flips you encounter must be even. And if I've taken L to be even, the number of frustrated bounds encountered should also be even, right? So that means on the dual honeycomb net, draw that here. If I walk like that, crossing bonds of one orientation, and I count the number of dimers I meet, right? Let that number in this case be N2, let's say. That number must be even, right? And in fact, you can check easily that if the dimers that touch are only 1 or 3 at every side, then this integer is preserved mod 2 along successive parallel lines. So it defines a sort of a winding number. So you can define these 3 winding numbers, N2, N1, and N0, which are just the numbers you encounter when you cross one row. And they are sort of well-defined mod 2, and you want them to be in the even sector for your model, for your dimer model to correspond exactly to the spin model. So the dimer model is actually twice as many states, roughly speaking, twice as many sectors as the dimer, 4 times as many, because it has even or odd parity in this direction, even or odd parity in this direction, and you only want the even combination. While 2 is enough to specify the parity. Right? The 2 directions in which you wrap is enough to specify the parities. In the case where you're at 0 temperature, where every link is touched by exactly one dimer, then actually there's a constraint that says, constant, right? It's equal to L square times some factor. So the third one is fixed, right? And when you have 3s, it's fixed up to, the parity is fixed, right? So there's one sector that exactly corresponds to the Ising model, and that's the sector you should study. This is just a detail I want to mention for completeness. Now we want to sort of think in terms of configurations of this dimer model to ask what's happening to the Ising spin. That's the ultimate goal, right? And this seems like a very long-winded way to do it, but you will see that it has some advantage. So the advantage is that it's the simplest example of sort of writing down some effective action for calculating things. So that's why I want to do it this way. So this constraint, let's take the 0 temperature case. There's exactly one dimer touching every side. and you're on the honeycomb net, so there's A sublattice sites and B sublattice sites. Right? So let's make up the rule that any link L on which there is a dimer has a magnetic field, if you wish, has a magnetic field pointing from A to B. Okay. So now you can ask what properties this satisfies. That translates from knowing that the total number touching it is 1. And you can see that the lattice divergence of B is 0. Okay. So the ground state constraint becomes a constraint which says some magnetic induction like field has 0 divergence at the lattice. Okay. Now if this was 3 dimensions, and we'll come to 3 dimensions in a bit, you would solve this by writing B equal to curl A and proceed, right? But in 2 dimensions, you don't really need the whole vector apparatus of curls. You can even sort of think of it on the lattice like this. You go back to the original triangular lattice and you define what I call height fields, which are scalar variables that live on the triangular lattice. These are not my original spins, although they live on the same lattice as my original spins. Okay? And you can schematically write B in some direction as this is the analog of curl A in 3 dimensions. In 2 dimensions, this is just the transverse gradient of some scalar, right? So on the lattice, you would do this more precisely. You would say that this B field is the difference of this height minus that height, and so on the lattice. And there's a simple lattice rule for this you can give. You can take a sublattice site and go anti-clockwise around it, like this. So supposing you knew the height here. Let's say you arbitrarily set the height to 0 here. Right? Now you want to find the heights everywhere else. That means you want to solve this. Right? You start with this and you want to go there, you go like this, anti-clockwise around the A. Okay? Every empty link you encounter, you go down by 1/3. So this becomes -1. Again, one more down, so that's another -1/3. Right? So 0, -1/3, -2/3, and every dimer you encounter, you go up by 2/3. So you come back. Right? On the B, it's the same rule, -1/3 for an empty link and +2/3 for a dimer, but not anti-clockwise, clockwise. So if you want this side, you go like that. And this way you can go through the lattice, and given a dimer configuration, you can construct a height configuration. Yeah, so 1 minus 1/3 is 2/3, no? Oh, sorry, how did that happen? So it should be, did I screw up somewhere? But NL is the lattice gradient, no? So you'll have to do this minus this. The transverse derivative with a minus sign because of the epsilon. So it's this minus this, that's +2. Okay? Yeah. So you can get a height configuration from a dimer configuration, and every spin configuration gives you a dimer configuration, but every dimer configuration gives you 2 spin configurations, because you can globally spin flip and the bond energies don't change. So you have to specify some corner spin and everything. So this is all extremely elementary, but more sophisticated versions of this play a role in other things as well, so it's good to introduce it. Okay. So are there any questions so far? No. Okay. So the next thing to ask is, what does that frustrated triangle correspond to, where you didn't do the best you could? So if you have a triangle like that, up, and up, You didn't do the best you could, and there are 3 dimers coming out like that. What does that do? So now you follow your going anti-clockwise rule, and you will go up by 2/3, up by 2/3, and again up by 2/3. And so when you come back, the height is no longer single value. Right? So there isn't a single valued height possible, there's a vortex. And this is a vortex that takes h to h plus 2 when you go around. Okay, so it's in some sense a double vortex. Okay? It's a double vortex if you define some angle theta as 2 pi h. And we'll see that this is a natural definition of an angle in this. Okay? All right. So this is all just rewriting things in different language, and we can't do much with any language so far, right? So what's the advantage? The advantage is now you start playing this game where you guess what is the form of the partition sum in these h variables. And the way you do that is a standard sort of thing we do in many contexts in physics. We imagine coarse graining this height configuration and ask what is the effective action satisfied by the coarse grained version of this configuration. So the idea is you break up your system. This is very schematic because I guess nobody really knows how to make this very precise. But you'll see that there are strong symmetry constraints that anyway restrict what the answer should be. So you imagine breaking up your system into blocks, and you allow local rearrangement of dimers within the block. Right? Anything that doesn't interfere with whatever are the things sticking out and connecting blocks. There'll be a few things that will connect blocks, some dimers that cross these lines. Those you don't change, but you allow all sorts of local rearrangements in each block. As you allow these local rearrangements, this H field will of course change, right? So you not only do you coarse grain over this region, this H field, like average it spatially, but you also average it over all the local rearrangements that are possible. Okay. And that averaged object we'll call little h. And little r will denote for us this coarse grained sort of continuum variable coordinate. And because you've sort of averaged over local rearrangements, although in the original problem every ground state had equal weight, so the partition sum at 0 temperature was just the sum over all states, right? Everything came in with 1. Now, if you want to write down a partition sum in terms of little h, there'll be some non-trivial weight function. So now, you will have z schematically as a path integral over this h times some non-trivial weight function, which you write in this standard form because you expect that the weight is a product, roughly speaking, of local objects, and so you can write it like this. Okay? And the goal now is to make some reasonable guesses or use some constraints from symmetries and other considerations to see what the form of S would be. Okay? So let's start doing that. So first imagine sort of the following operation. So let's say I have some region, and on its boundary there are some dimers, like so. Right? And there's a bunch of height variables inside that region. And let's say, without loss of generality, that the origin is here, origin for heights. So here's the origin, and I set h equal to 0 here, always. Okay. Now, more generally, this could be somewhere else, and this height is fixed to some number. Now, if I just change the state of the boundary, that's not going to affect how many different local rearrangements there are internally inside the region. I've drawn a very small region, but imagine a bigger region and lots of internal regions, right? So the weight function cannot depend on changing the state of the boundary by sort of rotating all these dimers by one shift. Right? But if you shift all these dimers by one, what's going to happen? What's going to happen is that instead of being able to go from here to here with a minus 2/3, because this is a A site and you're going clockwise, you would go from here to here with a plus 1/3. So you would change one of the heights at the nearest corner that you entered the region with by 1. And then if you change it by 1, since the relative stuff is anyway the same, all the heights would change by 1. Right? So h and h plus minus 1 are really the same configuration from the point of view of the weight they give to the partition function, right? So this is, h is like an angle, right? H is not a scalar variable in the usual sense. H is like an angle in the sense that nothing depends on shifting it by 1 or minus 1. Right? So, well, 2 pi h is an angle. So it's a sort of an angular variable in this sense, that the physics doesn't depend if you does not change if you change it by an integer. And that's the context in which taking an ambiguity of 2 in h, which is what happens with every frustrated triangle, corresponds to a double vortex. So we have an angle, and if you have these frustrated triangles, you have double vortices in the angle, but otherwise there are no vortices. No. Internally, nothing happens. No, so you're imagining, so this is the region you're coarse graining over to define little h. And all of them just change by 1 or minus. So that's one constraint. The other constraints come from symmetries. This is sort of a locality constraint that tells you that it's like an angle. The others come from symmetries. And I can draw some pictures for you, but you can draw them equally well yourself. So let me state the sort of basic results, and you can check some of it. So one thing you can check, so one easy way to check is to draw some simple states and ask how they change under symmetries. And for those simple states, count what the heights are and find the average height, right? So my favorite simple state is something I can draw very easily. I just draw these spokes going out like that, and then I continue the pattern. This is called a columnar state in the jargon, or Kekule state. And so on. So I can continue the pattern. So you can see it's sort of a threefold repeating pattern. And every A sublattice of triangles has these spokes going out, and B's and C's have these 3 dimensions. Right? Now you can see, supposing your origin is here for the heights are 0 here, fixed. This pattern will have average height h equal to 0. Simply because when you go here, you might go minus 1/3, and here you will go plus 1/3. So A sublattice will be plus 1/3, A sublattice is 0, C is plus 1/3, B is minus 1. Now I invite you to imagine acting on this pattern, but not the labels A, B, and C, with either a lattice rotation or a translation or any of the valid symmetries of the triangular lattice, and see what happens to each. And you should be able to convince yourself. I have enough time to draw. Maybe not. So if you just now take this pattern, this is a simple pattern which you can now translate, rotate, and work out the age. You will see that rotations correspond to this. And lattice translations, elementary lattice translations correspond to that. Okay? So those are the symmetries that come from the underlying microscopics, the global symmetries of the triangular lattice. And one last ingredient is again actually obvious from this picture. So let's compare this picture where the heights can never keep increasing if you go in some direction or keep decreasing in some direction. Right? They kind of oscillate back and forth. They go up, then they come down, then they again come down, then they again go up and so on. Compare that with, let's say, a pattern like this. In the standard jargon, this is called a staggered state. And it's actually a very special state in contrast to that one. Because you see, there's nothing I can do by way of a local rearrangement to connect it to another state. Right? It has no local loops of links which have occupied, unoccupied, occupied, unoccupied, alternate. If you had such a thing, you could flip it. And there's no ring exchanges possible over time. And so, if you have some region of space where locally the system looks like this, then the number of states that are going to contribute to S effective in that region are going to be very small. Right? So the weight is going to be very highly suppressed for every such region. And these are the regions you can see very easily by using our height rules that correspond to the height just being tilted on average. Right? So for example, this was plus 1/3 now. And now again it's 2/3 and so on and so forth. So the heights just run away. So the idea is that the effective action is counting how many local rearrangements there are inside the block. Right? That's the contribution. So you write integral dqx. Right? It's actually a product of terms, right? The integral in the exponential, that means it's a product of terms. So each local region contributes some e to the minus s local. Right? So if a region has very few states, the s local will be very large, and this factor will be very suppressed. Right? In contrast, if there are lots of states, then this number will be small or negative, and you will get a large contribution. Right? And so I've just hopefully convinced you that regions that locally look like the height is flat have lots of nearby states in the sense of local rearrangements, and these don't. And so there's a gradient cost in the effective action. You penalize large values of average gradient. And the standard constraints of analyticity then say that the leading term you can write down is a gradient H square. Okay. So now, if this part is clear, I can go relatively quickly. So I can now write the original partition function, which is just the sum over all ground states of the antiferromagnetic Ising model. Some constant, which I'll leave unstated right now. There's going to be one term like that, some positive constant in front. And then because I have these periodicities, h going to h plus 1/3, I'm also allowed some undetermined constants and higher harmonics. So that's the general form of the effective action. There's also higher gradients you can write down, but this will be the leading. Huh? Because H going to H plus or minus 1/3 is the same. Yeah? Okay. So now you see this is like a XY model on which you have sort of done a gradient approximation. And you're allowed to do that in this case because microscopically you're forbidding vortices. There are no vortices involved, right? Yeah, that's right. So this is like being in the Kostelis-Thouless phase, let's say, of an XY model with some stiffness. And then the only question that remains is there an ordered state? Because these terms lock the value of the angle to some value, right? Are these relevant or not? And that we know how to think about. That depends on the value here, the number here. So good way to parameterize that is, I think, to write this as and if you write it like this, then ignoring the effects of this term, assuming it's not important, you will get the correlator of e to the 2 pi I h going as 1 over R2 G. Okay? That's why I wrote it in that one. Okay? So this is like a XY model with anomalous exponent G, right? And you have to decide whether this anisotropy term is relevant or not, and that depends, of course, on the values. Right? There'll be some value at which it will first become relevant when G becomes small enough, right? And otherwise, it's not going to matter. Right? This is where we can go back to the 1950 solution of Warnier, who showed that there is no singularity in the thermodynamics as you come down to 0 temperature in the triangular Ising anisotropy. That was his result. He did not calculate spin correlations. I think it took 15 more years for people to use exact methods to calculate spin correlations. And they found that the spin correlations were certain kinds of power laws at 0 temperature and exponentially decaying at any non-zero. So we can never predict numbers by doing this sort of thing, but based on what we know, we would say that that system is then described by this term being irrelevant, right? And G being some particular value, such that it's consistent for this term to be irrelevant. Yeah, I mean, you can't predict numbers like this. Right? You can get this far and then you have to do something. You can catalog possibilities, right? So the possibilities are, it either has this sort of behavior or it's ordered, and we'll interpret both those possibilities. So for that interpretation, it's very important to ask, what is this fellow, e to the 2 pi? This field in this coarse grain theory, what does it correspond to the original model? So it's not hard to see just based on transformation properties of this object and comparing them to transformation properties of objects in the microscopic theory, that it corresponds to the following thing. You had your Ising model, and there are 3 orientations of bonds in the Ising model. Okay? So there are 3 kinds of bond energy variables in the Ising model, or equivalently 3 kinds of dimer variables in the dual model. Right? So those variables I'm labeling as 0, 1, and 2. So you can construct the following order parameter, bond order parameter, which is and you can check that this has exactly the same transformation properties as e to the 2 pi I h. So what this field is, it's really a representation of the bond variable, ordering at a certain wavelength in this 3 sublattice field. This is just the Fourier transform of bond energies at some particular wave vector. This wave vector in standard notation is the 3 sublattice wave vector. And using the transformation properties of H, you can check that this and that has the same transform. So if you write chi, more precisely, if you write chi as sum over R, some local variable chi of R, then you have the correspondence. Chi of R goes like equal to pi RH. So this tells you that there's a certain oscillation in the bond energy correlation in the Ising model that decays like this. It's oscillating at this wave vector. So there's a power law tendency to ordering at that wave vector, at least for the bond energies. We've not said anything about the spin. There's also a different power law for the uniform part that you get by recognizing that in addition, a given bond energy in some direction must have a piece which looks like this is what I would call the dipolar part. And I'm sort of purposely using the same variable B for the bond energy and for the magnetic induction I find. Right? So there's another piece which you just get from this more basic statement, which doesn't oscillate at any wave vector. It's a zero wave vector quantity, but it has funny dipolar property in terms of its correlations, dependence on angles, right? Because of this epsilon. Right? So there's a dipolar part to the bond energy correlators, and then there's this oscillator. There's two pieces. Right? So that's what you learn. But this maybe you don't want to think about bond energies. You want to talk about spins, and the spins are roughly speaking the square root of the bond energy. So again, you can do this symmetry analysis, and you can check. Let me now go here. That the original spin variable you can write in this language as a sum of two pieces with undetermined coefficients again. One is and the second is at wave vector q. So unlike the bond energies, there's no dipolar part to the spin correlators. They are entirely controlled by these. And so one general statement is that if the bond energies, so it turns out in the transverse field, in the Ising model of interest that 1 year solved, you know that sigma r, sigma 0 goes as sum a by r to the 9/2 plus sum b cosine 2 pi by 3 x plus y by square root. This is the exact result at zero temperature. At non-zero temperature, this gets cut off by an exponential. And this allows you to then identify what's the value of that g. You just work out what you get to get a 1 over root r. And the reason for this 9/2 and root r is simply because there's one term that's 3IH and one term that's 9. And in a Gaussian theory, this will have 9 times the power of that. Okay? So that's how you understand a two-dimensional case. And now let me sort of generalize this to go to the three-dimensional version of this, which is spin ice. So let me erase this. How much time do you have? Okay, good. Are there questions about this? Like what? Like this? Well, you put some weird interactions that are further neighbors that favor this pattern. This is a kind of a striped state on the, in fact, I think if you look at this polytope of silver nitride, because of further neighbor couplings, it actually orders in this stripy way, and in bond variables, it looks like. So there are materials that, if you translate to these pictures, would look like. And that's because of further neighbor couplings. So now let's go to 3 dimensions, to the pyrochlore lattice. And now we recognize that the ground state of the Ising antiferromagnet involves, so if I look at one sublattice of tetrahedra, the up-pointing ones, call them A, you would like to have two spins out, two in on this tetrahedron. Same thing on the B. So you can now define a fake magnetic induction, which again lives on links of the dual lattice, which is in this case a diamond lattice. The ones that connects the body centers via the spin. So now the spins lie on the bonds, right? So instead of this more complicated relationship between the spins and the magnetic induction, the spins are the magnetic induction. In the sense that you will say BL is sigma L minus half, with the convention that it points from A to B again. Okay. So, and sigma L has the convention that you take the up-pointing tetrahedron and a spin that points outward is +1 and a spin that points in is -. Okay. So that defines what you mean by plus and minus 1 here. And with that convention you have this BL which points from A to B. And again the constraint that you have two spins out, two spins in translates to lattice divergence of BL being 0. Okay. So now you are in 3 dimensions. Now you can solve this by writing B equal to curl A in the continuum. On the lattice you have to do some complicated thing about looking at the dual of this lattice and defining things that go around each link of the diamond lattice, but let's just work in this language. So now you have B vector that must be written like this. And again there is a question of what is, again you imagine you break the system up into blocks. It's the same story all over again. And you coarse grain over local rearrangements of spins, and all ground states start out having equal weight, 1. But then depending on how many ground states are accessible by local rearrangements, there will be some non-trivial weight function which will be a function of A or B, right? And you can check easily that if you have loops of spins that are up, down, like that inside the block, which corresponds to basically the B field going in a kind of a circle like that, then you have lots of local rearrangements. Otherwise you don't. That's just drawing some pictures will confuse you. So that suggests that there's a leading term anyway, apart from everything else, which gives you a partition function. Some stiffness curl A. Okay. And the prime just says, you should not worry about the fact that A and A plus a gradient are the same thing. The standard thing for gauge fields. So again, you can now ask, what does this predict for the original problem? And actually the calculation in some sense is easier because there aren't these e to the 2 pi h type operators. The magnetic induction B is the spin. So you just need to know what is the BB correlation function. In that simple Gaussian theory, right, which you can work out, and it's of course got a dipolar form, and you get a result that looks like, I guess, 3xv x mu minus r squared mu by r. You get the dipolar form times some coefficient. And this, if you Fourier transform the correlations, has a very characteristic, again, transverse sort of behavior in Q space, because this B field is just curl of something. So you can work out what the correlations are in Q space. And they involve this sort of singular behavior near Q. So, Fourier transform this, the answer going to the limit depends on which way you go, just like we did in 2D. That's the characteristic dipolar singularity. And that's something that is then visible in neutron scattering of these spinized materials. And that's a subject of many, many papers. They are called pinch points in the literature. They are just singularity, regions of singular behavior of the Fourier transform. And that can be visually seen very nicely in neutron scattering, which directly measure the spectrum. So you see, even at the classical level, just having this large ground state degeneracy allows sort of entropic effects, how many local rearrangements there are, right, to produce for you non-trivial effective actions that lead to very interesting spin coefficients, purely at the classical level. And this is sort of the classical analog, if you wish, of having large degeneracies quantum mechanically and then having some new physics emerge that describes the effective behavior of the system in that degenerate manner. So here this is just happening because of entropy. Yeah. So you are imagining putting a transverse field, for example, right? Yeah. So what's the question? You are asking why in 3D we don't order. So you're saying why is quantum order by disorder not so easy in 3D? Okay. Sorry? Okay, I need to think about this. I don't know why in 3D things are so robust. Well, less phase space. Maybe. Okay, so let's think about that. I'm not sure. I don't have a precise answer. Okay, so in the last 5 minutes, let me just say that something very interesting and similar happens even if you look at the isotropic case on the pyrochlore lattice. You again get dipolar correlators, but for an interestingly different reason. So now we are just interested in this simple model on the pyrochlore lattice. And as we discussed, there's a continuous infinity, two-dimensional continuous set of states for a single tetrahedron. And you expect that when you go to the full lattice, there'll be some continuous degeneracy of ground states, which basically obey the constraints vector sum of all spins, sum over I belonging to a tetrahedron, is 0 for every tetrahedron. Right? So you can actually, at the level of sort of writing down effective actions, do exactly what you did for the Ising case, and you will just have a O3 index alpha corresponding to a vector nature just floating around everywhere. But that is somehow maybe not as illuminating if I've already said that something like that happens in the Ising case. There's another way to think which is, I think, quite nice and instructive as a simple approximation, and that's the large n limit. Which is one of the few tractable non-trivial things you can do, either quantum mechanically or classically. So the idea is to say that we have n components instead of 3. Of these vectors, and instead of them adding up to s or 1, let's say they add up to n. Right? And we are going to take the large n limit of this. So instead of looking at the classical O3 model, we are looking at the classical ON model. But the same energy. So now, well, the way you impose, sorry? No, Hamiltonian is, so we're taking the Hamiltonian SI dot SJ. To begin with, we had classical unit vectors or classical vectors of length S. And now we are saying we're going to scale that length with n or with square root n, right? It has n components. That's why I scale it with n. No. So it's an ON model now. Symmetry is, these are ON vectors and you're taking the dot product over the ON index. So yes, you can write down all sorts of other terms maybe, but we are going to write just this. Yeah. Okay. So now we know how to solve this. I mean, you probably studied this in a StatMech course from Mars book or something. So you impose this constraint at every site by Lagrange multiplier. So you start with Z equal to integral S e to the minus theta j with the constraint, and then you impose the constraint explicitly by having an additional integral over a Lagrange multiplier variable. So integrating over lambda at every location forces the spin square to equal L at every site, right? And then we take a saddle point of the lambda integral, which means you're just basically replacing at large n, you're just replacing this by a number, I lambda by some number, which has to be self-consistently chosen. So you should solve the Gaussian theory where this is just a number, and then you should find out what number has the property that averages of a single spin at a site with that number equal n. So the lambda at which this is true is the correct lambda to use in the self-consistent Gaussian. That's how you do large n to leading on. So if you do that, you see that you basically got a, so this ON index just goes for a ride, you can just forget about it. And you basically got a quadratic form now. That's kind of the band structure of the tight binding model on the lattice you're at, shifted by some constant. Right? So if there's any interesting physics happening, it's got to be because of some properties of this band structure. I'm just saying it's a matrix which is a nearest neighbor connectivity matrix. That's all. So let's write it in matrix line. So let's write it in matrix language. So the partition function looks like so you can forget this now. And you basically have e to the minus, let's write it as a matrix, sum over ij, si alpha, eij plus some constant times delta ij is j. And in this simple Gaussian theory, you have to calculate this and ask that it be n. Right? The n will just cancel because n will just cancel because you will sum over n components. And the answer will be that 1 should equal T over J times the sum over eigenmodes of that matrix, and let the eigenfunctions be phi, right? So phi means I square, which are the eigenvalues. Right? So basically your problem boils down to calculating eigenvalues of this matrix. And that you can do by Fourier transformation. All you have to do is choose axes carefully so that you can write down the matrix in a tractable way. So I won't do that here. But this representation I gave you of Kagome planes is actually an ideal one. The easiest way to do it is to choose these as your axes. These two vectors in a plane and the third vector going up at 60 degrees. So if you choose those three vectors, you can work out this. And the interesting thing you find is that the lowest band is flat and doubly degenerate. And then there's some dispersing bands above. Okay? So you can see what that means in terms of this constraint. In the usual large N we do for ON models, the way you get symmetry breaking is that below some temperature, this equation can no longer be satisfied. Simply because there's a temperature in front that kills off this contribution and there's nothing left to add up to 1. And that's a signal of spontaneous symmetry breaking, of ordering. And then you know you have to introduce a condensate to fix it. That's how you do it in any standard treatment of any large N phase transition. So here you see, because there is a flat band, what the system will do is it will adjust the value of lambda SP so that the value of the flat band is order temperature and it will always keep cancelling. So let's write it again. Let's write it as a sum of two terms. Flat bands, flat band wave functions. And this number is going to be 0 plus something which is going to be order temperature. And then the rest of it which is order T. So in the low temperature limit, although it's true that this is going away and can't contribute to the 1, this can always be made to contribute and there's never a phase transition. So the macroscopic degeneracy you had in mind when you looked in terms of single tetrahedra and this non-trivial physics of cancellations that you were talking about reflects itself in this simple approximation as simply a flat band. And the fact that when there's a flat band, you can't order. And you can now see that ground state correlations, zero temperature correlations, are going to be determined by a projector into the flat band subspace. And if you work out the form of the projector for the pyrochlore lattice, that's again going to give you dipolar correlations, which is exactly the dipolar correlations you got. So here's a completely different approximate way, but instructive, I think, because it emphasizes the role of flat bands. That explains why these frustrated lattices have interesting physics. So with that, let me stop. Oh, sorry. So I'm just using the fact that delta of can be written as an integral d lambda e to the I lambda and I'm doing this at each site, so there's a different variable lambda I for each site I, and that's what I mean by this.
Any other questions?
Sorry? Right. Yeah. So I'm saying now I look for a saddle point, and the saddle point I look for is the uniform saddle point, and that solves the problem. And the value of the saddle point, the uniform value, has to be adjusted to solve this equation. Right? And in the usual case, in 3 dimensions, you always get a phase transition because you can never get enough contribution at low temperature from this mode sum. But when there's a flat band, the Lagrange multiplier will just adjust itself so that the flat band energy is just slightly above 0 of order temperature, so that you always get 1 from it. And that's how, in this large N way of thinking, flat bands gives you interesting physics. And the low temperature correlations can be thought of very nicely algebraically as projectors into the flat band subspace of the tight binding norm. So this is sort of classical version, if you like, of quantum Hall physics, where there's something simple microscopically, but when you project, you get some interesting. Okay, so you're projecting into the flat band subspace, that gives these dipole. Yeah. So tomorrow I hope to sort of start talking about quantum effects. So first, just sketch how you can put back in quantum mechanics in easy access limit, not spend too long on it. Then talk about things people have proposed, not me, other people have proposed for what happens for quantum mechanical spins with frustration, and introduce the idea of these sort of partons or slave particle theories and different kinds of variational wave functions. And then Subir has given me an assignment to discuss the toric code as an example. So I'll look at the Kitaev model as an example where these partons are exactly the right way. So it's all very elementary stuff. So I thought somebody should give elementary. Okay.
Any more questions? Well, then let's thank Kedar.